This is Jingfeng. I'm a research scientist at Recon AIP. Today, I'm going to host the TrustML Young Scientist Seminar. Before that, allow me to briefly introduce Recon AIP to our valuable guest. The full name of Recon AIP is the Recon Center for the Advanced Intelligence Project. AIP was founded in 2016 as a research center for the Next AIP project. AIP conducts Japan's leading AI research, which is headed by Professor Sugiyama. He's also a professor in the University of Tokyo. And AIP aims to enhance AI fundamental technology and its real-world applications. And we also encourage the collaboration with various researchers and engineers in related field. We will be very grateful if everyone here can visit us in our Nihonbashi office in the center of Tokyo in near future. Today, we are very honored and very happy to have our valuable guest, Irene Lee. She is also a project assistant professor at the University of Tokyo, and she obtained her PhD degree in the natural language processing at Yale University. And her main research is focus is on language modeling, transfer learning, and NLP applications in healthcare and education. Hi, Irene. Please get started.
Yeah, thank you for the quick introduction, Jingfeng, and thank you for the invitation. I'm really happy to take this opportunity and share some of my current research, and also looking forward to see if there are any chances for us to collaborate in the very near future. So the talk today I'm going to share is about transformers to GPTs. So before I actually start, I'm sure that all of you have went through. Okay, yeah. So if you have questions, please feel free to interrupt me or just type there so I can take a quick look. Thanks. So before I start my content for today, so I want to quickly briefly talk about large language models. So I think many of you have, maybe you have been using ChatGPT daily or very frequently in your daily life to help you to work or to help you to having fun or whatever it is. So as this is very popular for now, so maybe I'm not sure about the background of the audience, but I'll try my best to make it clear and to help you to understand the following content. So actually the large language models, they are based on a more basic model called transformers. So this is like a 12-layer, the fundamental model is a 12-layer neural network. And we'll see that recently the ChatGPT 3.5 and the latest version ChatGPT 4 actually can do a lot of amazing jobs. So for example, if I just type a question saying, give me the definition of large language models, it is able to generate a paragraph explaining this. So this looks like very amazing job that they can do. So back to the original, the fundamental model, transformers. So basically, it is a sequence-to-sequence model based on attention mechanism. So basically, it applies self-attention more. So for those who are not familiar with that, it's like you can imagine. So they're doing some matrix multiplication in the word embeddings, or in the middle layers or the hidden layers. So it's very complex, and it has it becomes bottleneck for the computation issue. So that's why they're really powerful, because they have so many parameters. And then transformers has become the fundamental architecture for later strong models. So there are many other branches to not only for English, but also for multilingual data, and then even for other subfields. So then So today the GPT family grows very fast, and it's originally from the first generation of GPT is the generative pre-trained transformers. And then applies very more complex structure, and it has it has an explosion in the number of parameters, and it also has stronger ability for dealing with longer inputs. So the GPT-3, I think there is the official a number about the parameters, about 175 billion parameters. But then for GPT-4, actually, I just saw the news yesterday. So it's still not the official release about how many parameters GPT-4 has. So there are some rumors saying it's about 1 trillion or even more than that. And then yesterday there is a news. I think a hacker actually went to a broadcast program and he said it's about 1.7 trillion parameters. So even it's larger than the guess before that. But still, we don't have an official number or from the team. And then it's very so after the transformer model, where you can see here, it happened I think around the year of 2019, and then soon it becomes like a big trend. So it was very funny because at the beginning people thought the transformer model is already very large, and then the BERT model, Roberta model, they're all very large. So people try to see how can I compress this model to make the size to be smaller, but still we want to have the same level of the performance. But soon after that, you can see GPT has, I don't believe they can draw the points in this with this kind of scale y-axis unit here, but you can imagine it's really crazy. So actually these 1 or 2 months, there are still very recent large, tech companies, they have so many new releases about their own large language models. So it soon becomes like a very competitive field. They're all releasing their own large language models. And then one amazing part from improvement from GPT-4 to 3 to 4 is that they can do multimodal tasks. So this is an example that I personally like it very much. So then the user just give an image as an input to GPT-4, and then it kind of like you can tell it's image from it's a photo taken from the user in his or her refrigerator. So then the user asks, so based on these ingredients, what can I do to make some cooked dishes? And then GPT-4 can magically, read, understand the question or the query, and then it can somehow understand what's inside this image. And then you can see that it kind of giving you the some recommendations, and there, I think I think those are very good recipes. So so this so this screenshot shows some statistics about GPT-3 family models. So some of them are focusing on one type of question, and some of them are focusing on some general tasks. So so then you can see that every I believe that every week, or not every month, every week or every few days, there are some new model that based on GPT came out. So then this is a really fast growing field. So so after this quick background information, I want to go through the main content for today. So so I will basically focus on 3 subtopics, including transformer efficiency, transformer explainability, and some recent observations on GPT 3.5 and 4. So let's first go to the move to the first topic, the efficiency of transformer. So as I just mentioned, so when the transformer model and there are like multiple layers and there are the attention heads inside each layer, it's very soon it becomes a bottleneck for the computation. And then so we have a paper this year in AAAI and tackling this kind of question. So the bottleneck is that the computation is becoming more and more serious, because when you have your input to be longer, it's gonna be really crazy. So when the BERT model, which is based on transformer, is a pre-trained model, when they first came out, they only support 512 tokens as the input sequence. So once you give it a longer sequence, then it just cut off at the 512 position. And also, so we say that, okay, this is only able for relatively short sequences. But then we always have the long sequence scenario where if you, for example, if you want to summarize a longer article, or sorry, so if you want to have some longer article as input, it's going to be like thousands of tokens as the input. So we have a quick statistic here. So we calculated the sum of the papers from the PubMed. So this is actually people publish medical or bioinformatics paper there in this website. And then the median length of each research paper is about longer than 4,000 words. And also, we always face the same problem in the computer vision domain, where you have your image in small patches, and it also exceeds the 500 limitations of the fundamental BERT model. And also, the complexity of computation and also the memory usage is crazy. So when you have your inputs to be the very fundamental one within around 500, it's kind of okay. But then if you increase your input to be, you can see like 4,000 or longer than 4,000 tokens, you can see that the GPU memory and the iteration or the training time becomes really crazy. So it's not like a linear thing, it's like an explosion in a quadratic complexity. And then, so why is that happening? Because the fundamental transformer model or a BERT model, they are using the full attention to calculate in each hidden in each layer. So the full attention is likely that you have your input as you have your input sentence, and then basically you have to consider each single pair of your token inside. And then they are doing very complex matrix multiplication. So that's why it's like really slow in computing. But is full attention very necessary? So here we have three different observations. So the first observation is that even though we calculate the attention value between almost each pair, we see that not all of the values are useful. Some of them are just very close to zero, doesn't really making any contributions for the final output. So then we think the attention map should be really sparse. And then the second observation is that so if you look at only one like a random token inside your sentence, we can see that these tokens are only paying attention to its neighbors or some tokens that are close to it. So then the observation we can see is that we may only need to focus on the local attention when we are looking at one target token. So we ignore some of the other tokens which are very far from this target token. And the third observation is that so in each input, there are always some very important or very important words or keywords that we may want to pay attention to, because imagine that you're doing a prediction task, and then maybe some of the one or two keywords are the reasons why you make such prediction. So in this observation, we think, okay, so, certain keywords, we need to pay attention to that from the beginning to the end. So these are called global attention. So based on these observations, we can simplify the full attention mechanism we can replace this kind of full attention mechanism with approximate sparse pattern. So then existing work also proposed some similar ideas to replace the full attention with sparse attention mechanism. So then they can reduce their computing complexity from big O of n squared to big O of n. And then, so there are two very famous model. One is called long former, the other is Big Bird. So then the long former, so actually this is, you can imagine this is the attention map. So if empty here, that means no value or no attention is considered. And then the orange color represents for the local attention. Then the blue ones are the global attention, just like I introduced previously. And the yellow ones, they are just some random values. And then the long former actually only focus on the local attention with the local attention on the diagonal value line here. So then they have this local window and they set a window size to make sure that they have a good consideration of the local tokens attentions. And then Big Bird has a little bit change based on long former. So then they have this local attention, but also they have this global attention, and also they also combine with the random attention to make sure that there are some knowledge happens in this white blocks. But not that much. So they show that with a little bit longer, with a little bit random attention, it's gonna have more robust result. So then we propose to, so then we propose to augment the sparse transformers with another method called attention diffusion. Targeting on the limitations. So the limitations, I mean here, so though they are very comprehensive in thinking about all the attention types, they are sometimes not really accurate in the approximation of the full attention mechanism. And sometimes the calculation is also very slow. And then also long former, as I mentioned, they have very fixed pattern and it has a very bad robustness in practice. So then we propose to use this attention diffusion method to calculate to approximate the full attention mechanism. So the idea is that we will first calculate the local values or the local attentions, which means we will calculate the direct connected pairs. And then we use certain ways to calculate the indirect connected pairs in a very fast way. So then actually you can see in the first step, we just calculate, and then in the second step, we quickly diffuse the values to try to have approximation in the undirected connected pairs. And then we do this kind of diffusion step multiple times. So then within one layer. So another graph view to help you to understand is probably in a graph diffusion way. So then let's see that. So this is a graph. So then you can see we have this blue node here in the middle. So this is our current target node. And then it has neighbors, and the neighbors also has other neighbors. So then in the first step, we'll calculate the direct neighbor values, attention values. And then we will, and then the values would diffuse to the neighbors of neighbors and even the neighbors of neighbors of neighbors. And then and then we'll have this graph diffusion way to fill our attention matrix at the end. So typically we still insist on the same type with Big Bird. We consider local, global, and random. But you can see we have this long former here, Big Bird in the middle, and this is our diffuser model. And like our diffuser model would have like smaller or fine-grained granularity in this kind of attention map visualization. And we also did a quick statistics in the sparse pattern by comparing the number of non-zero values to compare with long former and Big Bird. So let me explain. So here we have three rows. So depending on the length of the input, the tokens. So when you can see that the length is getting longer, and then the number of non-zero value from long former and Big Bird, they're also reducing. But you can see that when the length is about 1024, the long former actually have about 62% of the values to be non-zero. This is not really that dense. It's still like more than half. And also the Big Bird, it's about 55%. And our model, so the first column here is the total number of non-zero values. And then we show the local value, the local attention value, and the global attention value. And finally, this is the random. So then our model significantly have like less non-zero values in the matrix. And then when you can see the length is getting up to more than 4,000, while these are like 4,000, we still have a very low number. Also, we compared the when the sequence lengths are getting longer, we compared the memory usage. So like this line, the light blue line here, this is our model. When the sequence length is about 4,000, we don't really have that significant needs for the memory usage. But when you can see, we compare with other efficient transformers, they're all getting crazy about the memory usage. So given we're reducing the memory and also lower down the sparsity of the map, we still have a very good performance, competitive performance with the selected baselines. So I showed the two tests here. One is text classification. We basically tested on 5 different benchmarks, and these are extremely long context inputs. And then we have a good average of accurate F1 score here. We also tested our model with the question answering, and we all see that we're not. We're also have significant or competitive results compared with long former and Big Bird. Also, I didn't put tables here, but we also tested on we also test our deformer on image generation task, and also we tested on the long range arena. This is the especially the LRA benchmark. This is for this is designed for efficient transformers too. So we also have very competitive results. I think I'll stop here for a minute and checking if you have questions, just speak out, or yeah, I'll stop here for now. Okay, so there is a question in the chat. How the superable verb in German language is treated? Oh, so yeah. So if I understand this question correctly, so like German words, they're pretty long, right? So you're wondering how this is chunked, or how transformer deals with this. So it's a really interesting question. I think German is also a typical case. But actually, so when you have a word in in a context, then they initially we have a way to chunk them based on statistics. So which means let me draw something here. Okay. So let's say you have this verb here. Let's pretend this is long. So so based on the statistics, there is a vocabulary list that can tell us where to just chunk them. So these word stems, it's calculated based on a very large corpus. So we sort of know that, okay, we should chunk here because it's a very popular stem for the words. So basically that's like a rough answer to this.
I have questions
Yeah.
in terms of sparsity in transformer. I noticed in maybe 10 years ago, there has some sparse Gaussian process, kind of like reduce the full computation into the sparse computation that can speed up. So is that possible to use kind of sparse Gaussian process to interpret, the tension computation, and also perhaps make it even better, I guess. Perhaps
I think thanks for the good question. I think currently the efficiency transfer, they're all using very simple ideas. They don't, I'm not sure, I don't think they even reach that far. So so this way is that they just try to see, okay, we have to so it's a very simple math question. So we're so by approximation, I mean, let's say you have a very complex attention. This is sorry, a very complex matrix. Yeah, and then they're just doing decomposition. I want to make it as B multiplied with C, and then and then you can see there, like, maybe the dimension is reducing. So that's like a big mass they are working with. They don't really have like statistical way or something like that you mentioned.
Yeah. I guess because I look at these figures, it's give me the strong feeling that the sparse Gaussian process can do the sparse decomposition to a full matrix to that probably that's a comment. Yeah, thank you very much.
Yeah, thanks. Yeah, I believe I'm not sure if there are some ongoing work that working with that, but I mean these baselines we're compared with, they're like based on very simple, not very simple, but I mean simple but effective ways doing decomposition of the matrix. So they're shown to be very effective for now. But I'm looking forward to see if there are, the method that you mentioned. Thanks. Yeah, so okay, I see a follow-up question in the chat. At some time, not so long future, most literature than human. Yeah, what AI do? I think this is a really interesting and nice question. I want to save it to the end of the talk, so because I may have some similar contents at the end. But thank you for the question. For now, I will have a discussion before my in later content. Yeah. Okay. Keep going here. So then in the second topic I want to discuss is the explainable transformers. That sort of it's a very interesting question, because people are always talking about this when the neural network came out. So people don't understand what's going on, and it has long been a black box, and we try to understand the mechanism inside it. And then the language models are getting huge, and then we don't really know what's inside and what is the magic inside it. So in this topic, this is a work we just submitted to a conference, but I sort of I cannot tell you 100% what's going on, but I want to show you some interesting findings. So we try to explain the outputs of transformers from a linguistic perspective. So by explainable transformer is, I mean, we wish to understand what is the relationship between output and input by providing the interpretable outcomes in between of the output decisions. So then our focus would be, we studied the fundamental transformers, and then we play with the attention head or the matrix that we talk about. And then we just visualize those attention values and try to see which kind of tokens the attention values pays attention to. But interestingly, we achieve this from a linguistic point of view. So the linguistic point of view, it's like we look at certain types of the tokens from the like more linguistic way. So so we summarize four different dependency relations in English from an existing data set. So this is I believe this is like a standard data set containing multiple like most containing English vocabularies, English literature. So we focus on four types. So these are nominal subject, direct object, adjective modifier, and adverb modifier. So I put an example here to help people to understand what are those. So imagine that we have an example sentence that goes, "She likes eating delicious sushi rolls with chopsticks." So in this sentence, the nominal subject is the word "she," and then what happened to this subject is the sushi rolls. So the sushi rolls would be the direct object, and then there is an adjective modifier, which is the delicious, and finally there is the adverbial modifier is with chopsticks. So how does the event happen? It's with the chopsticks. So you can see that we use this for we focus on these four types of dependency relation. So that basically happens in almost all of the sentences. And then we then did a visualization on the chosen on 5 chosen data set and try to see what are the attention values pay attention to. So so the y-axis here, this shows the different layers of the transformer model. So the upper layers, so it's from the top to the bottom. So the top layers are former layers, and then the bottom layers are later layers. And also there are about 12 different layers, and then for each layer, you can see these on x-axis shows the number, so shows the attention head. So there are individually 12 different attention heads, and they are learning something differently. So this is the way that we calculate the attention. And then like each block here shows different types of the perspective of these dependency relation, and we also have a positional positional type to calculate, and then so these are based on statistics. So what we can see is that in the former layers, you can see they're all like light green, which is the positional type, and then so the positional type is actually the position of the word, and then so you can imagine this is like a spatial information of the word. Then in the later layers, it kind of pays more attention to this kind of dependency relations. And then you can see, especially this last image, it pays, I think, almost very much attention to the adverbs and also the second type, the direct object. So then this means that they kind of understand the meaning of the sentence, and then they try to make prediction based on the content or the linguistic content or the relations within the word, within the sentence. So to make this more interesting and clear, I also put some examples here. So then this is an input example from the QQP benchmark. So the task is we're given a pair of sentences at each time, and then we try to predict if these two sentences are presenting the same meaning, or do they mean the same thing? So it's considered to be a very easy task by visualizing the word importance by showing the different colors. So the darker color or brighter color means more important, distinguished by our model. So then the first case, I think this is too easy. So it says, is there a reason why, blah, blah, blah. And then the second sentence is, what are some reasons, something, something. And then we highlight, our model highlights the words why and should, and then the second sentence says reasons. Also, you can see that in the first sentence, it also has the word reason somehow is highlighted. So then this is like how, so what we're doing here is we just try to highlight those tokens on why the model makes such prediction. So in this case, green means yes, so it's a positive prediction. So, and then we want to ask the model why this is a positive case, because you can see that we highlight those words that we think it's more that we think it's more important to make the prediction. And then another, maybe we look at the second example here. So this is the we're given a text, which is I think it's a review from a user, and red means this example is classified as negative prediction. So why this is negative? Because we can see that our model highlights the word unfortunately, which is very negative word in semantics. And then also they say something is very, it's missing or miss, and also these, they avoid something. So these are all negative words that we highlighted. Yes, so in general, like we try to have a score for this each individual token, and then we try to have an explainable output of the final prediction. We also did experiments for question answering and some other interesting tasks, but I don't. But since this is a submitted work, so I just have showed some interesting findings, but not giving more details. Okay, so the last topic I want to go through is some interesting observations in the most recent GPT 3.5 or 4 APIs that we tried. So we're in this observation, we're especially interested on the ability of the ability for zero-shot inference for some certain tasks. So we choose to let the model to give us some definition or clarification on some concept or on some words inside some context. So for example, here we give some inputs, and then we ask GPT 3.5 to generate the definition of a target word. So so this is the first paragraph here. This is our inputs. So it's especially picked from a clinical background information. So it's very very domain specific. And then it mentions some word, which is the CNS, this keywords. And then we ask, given these contexts, what is the definition of CNS in the given sentence? And then GPT can sometimes explain this very well. We tried with different cases, but not every time GPT can get it. So these tasks are very useful, especially when you want to learn something, when you want to clarify something, or when you just simply ask the definition of something. So then we especially interested in this explanation part, and we also focus on the quality of the generated definition of GPT models. So what we first did a quick evaluation on the zero-shot ability for that. So so then we simply give this kind of prompt to the GPT 3.5 using that API. So we first give the sentence, and then we simply ask, okay, given the example, what is the definition of something in one sentence? And then there is a benchmark to evaluate the generated quality, totally automatic matrix. So then it's called the WIC data set. And then we tested the GPT 3.5. Actually, this is without any training. So just let it to do a quick inference on the WIC data set with our prompt. So it's the accuracy is about 70.5. And then the table shows the recent SOTA performance of this benchmark. So I would say that it really has a very good zero-shot ability. So you can see it's almost like the third place without any training, which is very impressive. But these are, I believe, these are well-trained models, but smaller models. And then, so given the automatic evaluation being very impressive, then we will focus more on the quality of the generated text. So then to make this evaluation more interestingly, so we just let the GPT model to generate a definition of given concept based on different background of people. So by different background, I mean the educational background. So we pick the law domain as the test vocabulary. So we give a very, like, I don't even know the definition of the words, and we just ask GPT to generate some explanation given for this query concept. And then we say, okay, generate this for primary school people, or generate the explanation for master degree people. So we tested with different backgrounds, and then we let those people to rank or give ratings to each different versions, or based on many different perspectives. For example, fluency, or how do you like it or not. So then we have very well-defined criteria for this, and then we also studied the generated outputs because this is still ongoing, but we wish to have some human evaluation later. But for now, we have a way to calculate to have an automatic matrix to look at these generated outputs given different group of people. So so this measurement is called FKGL score. So this is to measure how difficult the text is for different people to understand the text. So also this is I think we're using an English version, but I'm not sure if other language have the similar criteria. But so for English version, we calculate this FKGL score, and then lower score means it's pretty easy to understand. A higher score means it's pretty hard. So it ranges from 0 to 18. And then you can see these are help people to understand. So if you read the novel Harry Potter, like the vocabulary written for that novel is in an average value, which is between 6 to 9. And then so if you are really well trained, then you can read academic paper, then the FKGL score reaches to 15 to 18. So this means the difficulty for the text And then because we studied the different groups, and then we let the GPT to generate definitions for different groups of people. And then with our findings is that here we compared elementary school, high school, and master people, the master degree people in college. So we can see that the FKGL score is getting higher because of the, the vocabularies are more harder to understand. And then in the elementary school, it tends to be easier. But the fact is that the general public should aim for the score of 8. It's the general public. In English, if you read newspapers, and like very general, so you have to make the public to understand what's going on. So 8 is FKGL is 8, then it means like an average level. And then you can see 8 is still, you can see that these are the GPT generated outputs. So even for the elementary school, it kind of reached the score to be 10, which is typically not an elementary school people should have. And also the high school is pretty like very high, and also the master score it's very close to 15, which is the requirement for reading an academic paper. So the finding shows that GPT actually, the model thought that we are much smarter than the public. So then I think that even though the GPT can sometimes explain, do the job and explain the word to us, but the generated output is still, the quality is still something we're worried about, and we still this is still an ongoing work. But for now, we see that it tend to use harder words to explain to give the explanation of the given vocabulary. Okay, so back to the big topic of large language models, and also I'll soon answer the question in the chat. So it's getting crazy these months, and for the large language models, and then people researchers, they look at what we can do for this kind of new trend. So this is a very good reading material. So it's they collected some PhD's perspective on the NLP research for the large language models, and I personally picked some points which I think would be interesting. So in general, there are still the data is training data or whatever kind of data, like good quality data, is still should be considered as a very important thing. So they see that using LLMs, sometimes they perform poor on the low resource language, because they during pre-training or fine-tuning, they don't really have such massive data for the low resource languages. And also for some certain domains, educational, healthcare, or law domain, they still think the data is they still think they're lacking kind of these kind of appropriate data in domain-specific tasks. And then finally, we're using the services, I think, from the LLMs. So to build a better online environment, there are many plugins coming out that can speed up people's work efficiency, and also to speed up learning process of people. So previously we have been working in a very similar, I would say we try to help people to learn something really fast, because we have we have certain manually collected data, and it's pretty large, and we try to do something like this. We try to see, okay, today I want to learn something. I want to learn what is the topic. I want to learn the topic text summarization. So this is a term this is a research topic in natural language processing fields. And then you imagine that you have no knowledge on it, and then you probably want to check the textbook, or you probably want to just simply check the wiki data Wikipedia for a very quick introduction. So we design our pipeline to achieve this goal. So you can just type in the query topic to be text summarization, and then we have our model to generate a whole Wikipedia style survey generation for this. So this table here shows the content that our model generates. So it clearly has different sections. For example, here we show the introduction of the concept, and we show the key ideas of that, and also we show the application of that. But this was very hard. As you can see, we have a whole pipeline for this, and then we have it to be 2 different steps, and then I'll skip the details, but what I want to say is that before GPT, it was really like an engineering thing, and we make it a whole project to do that. But today, obviously, I just show some examples, and GPT can do this very easily. I mean, probably not very perfect in quality, but you can see it certainly has this kind of potential ability for this. We also using our data, our pipeline to achieve some other smarter ways of learning. So one example is we try to figure out the relations between the concepts. So this could help people to learn something really fast so that you can follow a path during your learning. I think I'll skip this for now. And then, so a quick overview for the talk, a quick summary for the talk today. So I went through the efficiency of transformers, explainability of transformers, and also we talk about a little bit observation for GPT-3 and 4. So what I want to summarize here is that the ChatGPT-like models it is getting crazy, but then we still think there are some interesting things we can do for domain-specific GPT models. Why we want to do domain-specific things? Because because we want to utilize the specific domain knowledge inside this large GPT models to make it more suitable for your personalized problem using your own data. And also we want to make like a GPT level model to be open source, especially when we have this specific domain knowledge within the large language model. And also we wish to have a safe or privacy thing. We want to have this a very safe model that can run locally. Otherwise, you need to call their API, and then your data would go through the internet, which is very dangerous to some extent. And then, so then this example here I'm showing. This is the recent work. This is called Chat Doctor. So users can ask what's going on by given some descriptions of the user. So imagine that you're talking to a doctor, but the doctor is obviously it's a trained model. So the chat doctor would give you some interactions or some suggestions on your medical questions. So this is kind of the like domain specific GPT that I'm in here. Also, okay, so I think this is all my materials for today. I'll first go reply to the question in the meeting in the chat. So the question from the audience is about, yeah, so the question is AI would have obtained almost all literatures. I think this is partially true because yes, it almost read all of the web data and it obtains knowledge really quickly and fast. And after that, AI should have nothing to learn more. What AI should do. I think this is pretty interesting. AI should have nothing to learn more. So I think my answer would not be correct, but my perspective, personal opinion is that as humans, we're creating something new. So I think there was a paper talking about this. So even though you give all the relevant papers to the model, and then you ask the model to summarize something, the Newton law or some physical law, it cannot do that. So I mean, AI learns something, but it really like not that perfect as people imagine. Also, I don't think it can have ability to create something new in theory or something really crazy thing that can help people to achieve more advanced achievements in physics or in some other scientific field. So this is I'm not sure if this answers your question, but I'm happy to discuss more with the audience. Yeah, so I will stop here, and I'm happy to answer any questions. Thank you.
Thank you for Irene's great talk. I have a questions. Yeah, can you go back to the previous slides for the domain specific?
Yes.
Do you use a fine-tuning strategy, or you train from scratch a large language model for domain?
Right. So yeah. So we took a pre-trained model. It's I think it's released by Meta, so it's a pre-trained model, and then from that we have our own data and then fine tune it, and then we design some interesting tasks to fine tune it.
It's the Hugging Face downloaded from that.
Yeah,
right?
kind of. Yeah.
Yes. But then the follow-up question is, there's a fine-tuning, they have several strategies. For example, the whole fine-tuning, you also touch the fundamental parameters of large language model. You can also calculate a small part to fine-tune that small part, or you even do a few short learnings without touching any. So which one do you think is more effective to domain-specific applications, or that depends on applications? What do you think?
Yeah. It's an interesting question. In general, it's kind of a trade-off. So depending on your data quality too. So if your data is really large, and then obviously we did some tests. So if you have a very large scale data that you want to fine tune, you can choose to fine tune every single layer. But if your data size is very small, in this way, it's very dangerous for a model to memorize what's going on. So it's very easy to be overfitting with the data. And then when your data is small, we tend to only fine tune, I think, the top few layers for the task. Yeah. So, but also it depends on your server, your computational resource. So obviously, if you fine tune every single layer, it's gonna take longer in your experiments. It's more complex.
It's kind of some optimal strategies. Maybe this can support this kind of claiming or something. I guess no, right?
I believe there are probably some frameworks to help you to speed up this part. Yeah, but in practice, I mean, in our experiments, we'll just try a few settings, and then I don't think I have more smarter ways, but yeah.
Okay.
Thanks.
I noticed another question from chat box. Can you?
Yeah. So when we say we really get change of. Yeah, I think I'm not pretty sure like the speech. So I believe the question goes for that LLMs or GPTs they trained on the web data and web text data. So you're saying the audience have a question on the speech data too. I think there are models tackling speech or even image data for fine-tuning or for training. But I'm sorry, I don't really specialize in that kind of model, so I'm not sure I can answer this. Thanks.
Okay, then if there's no further questions popping up, I think that now is a good time to end up today's seminars. And we also hope, Irene, you can visit us in the future, our office in Nihonbashi. Then thanks again for your great talk today.
Yeah, thank you so much.
They can email you.
Yeah, thank you. Yeah, thank you so much. Thanks for the invitation. It's a really nice chance to discuss with you. Okay.
Thank you.
Thank you. Bye.